Alrighty. Now, just a couple things before we move forward on this slide here. And yes, I did change the title of this slide. If you notice from the end of the last video to this video, you're not going crazy. I did change the title. So I just want to remind you a few things about temperature and then how that relates to density. All right. You're used to hearing that perhaps that things expand when they get hot and they contract when they get cold, right? Well, that's due to this first bullet here. First of all, remember that the temperature is a measure of molecular speed or particle speed in this case. All right. Faster something is moving, we'd say it's hot. The slower something's moving, we'd say it's cold. Okay. So what we're adding to that is the idea that the faster a particle is moving, the more space it puts between it and the particles around it, kind of like you're supposed to do on the highway. The faster you go, the more space you're supposed to have between the cars around you. That is a law of nature. I wish it was a law of nature on the roads. Every so often I do like to keep my space between me and the car in front of me, and there's always some moron that wants to pull in there because I left some space. Drives me bonkers. Anyhow, can't break that law in air molecules, okay? So what happens here? Remember that little puffy little cloud I had you draw on your paper, right? Imagine that that's full of air molecules. Or let's say there's 100 of them. When you heat that up, those air molecules are going to expand. Now, I don't want you to expand mentally the size of your cloud there, but we want the air molecules themselves to move farther apart because they're getting hotter, they're moving faster. What that means is you're going to have less air molecules in that same outline of the cloud. You follow? Now, let's go back to the cloud at just its normal temperature, and then let's cool it off. Those air molecules are going to be able to go closer together, which means more air molecules are going to come into that same amount of space if you allow it. We want you to allow it. So we're going to pack more air molecules in. So what we're saying then is that air temperature plays a big role in the density, okay, mass per volume, right, of a parcel of air. So just keep that in mind. All right. Why does the wind blow? Well, first of all, I guess what is wind would be a good question. And wind is air moving from areas of high pressure to areas of low pressure. All right. So these parcels of air that we've been talking about, if they themselves are in a high pressure system or situation, and the next parcel over is in a lower air pressure system, it's gonna want to move. Just again, a fundamental law of nature. It's going to move from areas of high pressure to low pressure. All right, and to help you visualize that, I've got a little YouTube video here. Probably all familiar with this. All right, play that again for you real quick. And I want you to think what's happening here. Or more so, why you think it's happening. Why did the air come out of the balloon? Well, you probably are going to say because the balloon pushed it out, right? The elastic nature, the rubbery material that the balloon is made out of, it pushed the air out as it wanted to contract back to its normal size. I'm sure you were going to say something along those lines. And that's all very true. But it's also true that you're going from a high pressure area to a low pressure area. The area inside that balloon is definitely under pressure caused by that elastic wall. So when you take the pressure off of the nozzle, we'll just call it, the end of it there, it allows the air to escape to an area of much lower pressure. Okay. So again, it's hard to visualize in with those puffy little clouds. It's hard to visualize if you happen to be looking out your window or across your room, and you don't see those dividers between the parcels of air, but they're there. All right. Okay, so I made a couple changes here. The sun doesn't heat up the air itself. It really kind of just passes through majority of the atmosphere without, temperature-wise, without affecting the temperature of the air, the molecules. Okay. What happens instead is that the sun heats up the surface of the earth. And there's a mixture of three things here, all of which need to happen for that energy to move upwards, back up into the atmosphere and warm up the atmosphere. We've got conduction, we've got convection, and we've got radiation. Okay? And as I just said, we need all three of those in conjunction with one another. And conduction is energy transfer through touching. Okay, so and I'm oversimplifying things a bit. Please forgive me, but we do have an entire PowerPoint on energy transfer in the atmosphere, which we'll talk about more in depth at some point. So the surface of the Earth heats up the air that is in contact with it. Just a tiny little covering. Okay. From there, we rely on convection to move that energy up into the atmosphere. Remember, convection is the idea that warm air rises, cold air sinks. So the ground heats up the air through conduction. That air then rises, allowing cooler air to move into its place. And then lastly, we have the process of radiation. And with radiation, we've got bodies that have absorbed energy, in this case, the Earth, radiating or emitting, energy, kind of like a radiator. If you've ever had a house or been to a house that had a radiator, warm up the water, and that it radiates heat. Now, with regards to that, it's important to keep in mind in the whole energy balance of things that on the average, the sun only heats up the surface of any given surface of the Earth half of the day, yet it radiates all day. So we'll use numbers, just making up numbers here, but let's just say any given surface of the Earth only absorbs solar energy for 12 hours a day, but that same surface radiates energy 24 hours a day. So it's almost a losing game, so to speak. All right. We're not going to get into talking about energy budgets and all that stuff, but it can get rather complicated. This is just sort of, we already talked about this. Seems out of place at the moment here, but just a reminder, I guess. That temperature is particulate speed, and just reminding you that air consists of little particles. All right, cloud formation. Good stuff now. Cloud Journal is always one of the exciting labs that we do for a lot of folks. For one thing, it's not hard. You understand it. And actually, the more pictures of clouds you take, the more you seem to enjoy it, and that's cool. I love giving you guys labs that you enjoy for a change. So have fun with the Cloud Lab. So recall rain formation ideas. We did touch on this with the water cycle, I guess, and the idea that that as water evaporates from the surface of the earth, it goes up into the atmosphere where it cools off, and it condenses back into water droplets. Those water droplets go together and through their own sort of gravitational attraction eventually form what we've come to call a cloud, right? And then those cloud drops continue to get bigger and bigger and bigger until they are too heavy to be held together by that cloud's sort of microgravity. And at that point, the cloud starts to fall apart. The raindrops, we'll just say in this example, fall back to Earth. So it's that process of convection that allows the warm, moist air to rise. The sun warms up water. Some of that water evaporates, rises up into the atmosphere. It cools and condenses, turns back into water droplets. Okay, clouds are made of water, liquid water, or ice, but not gas. They're not water vapor. Anyhow, that's one of my little stickler things I really want you guys to remember. And then, again, as the cloud droplets get too big, the cloud starts to fall apart. Water falls back down to Earth. This is something we call precipitation. Okay? So that's recalling the rain formation ideas there that were discussed during the hydrologic cycle or the water cycle discussion. And yeah, I just explained that. Give you an idea of how big raindrops are compared to cloud droplets, or more so give you an idea how small cloud droplets are. Okay, not that you could probably picture 0.02 centimeters, but you know that it's a really small number. And the idea being that we need a lot of cloud droplets to form together, to merge together in order to become a good-sized rain droplet. Alright, I'm going to end this one here before we start the cloud types conversation proper, because that'll take us over our time limit here.